Hi everyone, my name is Dishan Tariq and here are my group mates Kashif Rahim and Frederick Suzai. Today our presentation topic is the pitch angle control of an aircraft through servo unit by the flapper angle control. So we are controlling the flapper angle by which the pitch angle control of aircraft by just a servo system, servo motor, right? And it includes the designing and implementation of control system and the process of this process is used in the control industries, in robotics, in automations, food beverage companies, and this technical project is mostly concerned with the modeling, design, and development of the control system. So here is the transfer function. First transfer function is for the aircraft dynamics, that is KDC by tau s plus 1, and then the transfer function for our actual flapper, which include the dynamics of the aircraft and a servo system and complete servo systems output, like its inductor, its resistor, its capacitor, everything. Then we have here, these are the parameters that we are modeling. One is servo inductance, denoted by L, then shaft movement by J, then armature resistance, RA, then back EMF constant, KE, then the motor constant, torque, KT. Here is our design methodology. And if we see at the right hand side, the servo and the servo unit and the aircraft, this is our model, this is our system. And we have this controller before our system, PID controller. This is our design diagram. So that's a closed loop system and with the unity feedback, right? So here is like our Simulink model, which has this first step input. Then we have unit servo flapper, and then we have an aircraft dynamics. These are transfer functions. And we at the end we have a scope by which we are observing that include pitch angle as an output control. So here is output of our open loop system. If we run our system with only this model and we don't use our feedback, we can get this response of our system. Now, Kashif will explain the further closed loop system and further in the presentation. Thank you.
Thank you, Zishan. So I will carry on the open loop system. Here you can see the poles, the two poles. One is at number 2 and the other one is in -10. You can see that they do not have any significant effect on the output as they lie on the real axis. But there is one pole that lie on the origin that will affect the output, but it will be unbounded and unstable in the nature. This is the closed loop system in which you can see we can add the feedback at the initial of the system so we can calculate the error. For the type 0 system, these parameters are often calculated for second order underdamped system, but the system we have currently right now, it's aircraft angle pitch. So it's an example of higher order system like third or fourth order system. So it is very necessary to create, build and fine tune the controller so that we can achieve the output results as per our desired, like low settling time and with the low steady state error. Uh, Here we can see there are basically we have three PID. These three are compensator. One is proportional gain, one is derivative gain, and the third one is integral gain. There are two methods for tuning. One is manual tuning and the other one is auto tuning that is done by the AI system at the MATLAB. By adjusting these three PID parameters, we can achieve the stable system. We can avoid the steady state error as well as we can have the less settling time and less overshoot to achieve our desired results. Here you can see the output response of closed loop system. So you can see we have compared the open, when we compare the open loop dynamic model that is without any controller. With the closed loop, you can see in the closed loop there is minimum overshoot, as well as you can see the settling time is very less. It's around 4 seconds. In here we have basically compared the manual control and as well as the auto tuning. So the the second column of the table, it shows the manual control, and third column of the table, it shows the auto tuning. So you can see the peak overshoot, rise time, settling time, and steady state error. Everything is less in auto tuning, while everything you can see as compared to the auto tuning, it's much greater in the manual control. So as a result of this summary, we can see the robust PID controller, it's superior to manual controlling of PID parameters. Thank you so much. So Frederick will carry on this presentation.
Yeah, thanks, Kashif. So when it comes to the AI reflection side, during this project, we integrated AI, specifically ChatGPT, as a support tool throughout the modeling and control design phases. It was especially useful for validating our transfer function derivations, ensuring the correct application of Laplace transforms to both electrical and mechanical dynamics in the servo and aircraft models. The AI was offered detailed insight into the system's pole zero structure. It helped us understand why the open loop response was unstable, specifically pointing out the significance of the pole at the origin in the making of the system, type 1. When transitioning to Simulink, ChatGPT provided structure for building the model effectively and assisted in designing the PID controller using the CISO tool. It broke down the influence of proportional integral and the derivative components on rise time, overshoot, and steady state error, aligning well with our design criteria. To maintain accuracy, all AI guidance was cross-checked against textbook and simulation outputs. Overall, AI acted as a technical mentor, enhancing our system understanding and reducing development time. Thank you.
Thank you, Frederick. So here is all of our project that the Frederick just finished explaining. And in conclusion, we can say that we have designed an unit servo unit flapper of angle control for an aircraft, and we have modeled it first. Then we tuned it with PID controller. Then we made a Simulink model, and then we check the AI that how it reflects. Thank you very much. That's all from our side. Yeah, that's it.